Thanks for letting us talk here and visit this extremely pleasant city, which we haven't been to before. We're very impressed by it. Okay, induction and deduction in statistics. This is something that we're excited about. It's something I've been trying to put together for about the last 15 years, and we did it in time for the conference, so it was irresistible to show it to you. Okay, so one of the reasons why this is important is that the distinction between induction and deduction is, in a way, the first cut in Western philosophical pie. So here's where it happens explicitly. David Hume in the Inquiry, in the very salient section just prior to his discussion of the problem of induction, says, all the objects of human inquiry may be naturally divided into two kinds, to wit, relations of ideas and matters of fact. Okay, so that's the discussion we're talking about. Here's Rudolf Carnap saying almost the same thing. Any inference in science belongs to one of two kinds. Either it yields certainty in the sense that the conclusion is necessarily true, provided that the premises are true, or it does not. The first kind is deductive inference, and the second kind will be called inductive inference. Okay, so that's a very similar cut in the pie. So, to simplify a little bit, deductive inference, what is it supposed to be? It's truth-preserving. That's something that Carnap said explicitly. If you talk to our colleagues in computer science, they will emphasize its stability or monotonicity, which means adding premises never loses conclusions. And in philosophy, we tend to, philosophy of science in particular, we would say is non-ampliative in some sense. The conclusions don't go beyond the premises provided in terms of the information they contain. And then inductive inference is anything else. It's not deductive. So if you perform an inference that doesn't have those nice properties, it's an inductive inference, and it's necessarily going to be more risky. Okay, so in the philosophy of science, this is important because we can distinguish various kinds of scientific inferences and classify them, we hope usefully, into one or the other. So deduction would include calculations, but would also involve refuting a universal hypothesis with a counterexample, verifying an existential hypothesis, deciding between two universal hypotheses, predicting data from a universal hypothesis, or determining whether hypotheses are compatible with data E. So all of that stuff would be deductive. Induction, on the other hand, would include inferring a universal hypothesis from data, or choosing one from maybe an infinite range of possible alternative hypotheses. Right? So that would be theory choice. Okay, and so inferring the universal hypothesis from data here we'll recognize as posing Hume's problem of induction. What justifies it? Because the universal hypothesis always extends the data provided to an infinite degree. All right, so that's definitely a case of ampliative rather than non-ampliative inference. Okay, so much I think should be pretty uncontroversial. You may wonder how often any of those things happen, but if they did happen, we would probably classify them as I've done here. However, this whole classification depends on deterministic data. Okay, so that the theory determinately implies what will happen. But if the data are stochastic, so that we're in a statistical domain, then things shift. So if the data are stochastic, notoriously, no statistical theory logically entails that you'll get a certain sample. Right? It only implies, maybe, if you're lucky, that you'll get a sample with a given probability. Okay? So that doesn't mean that you'll get it. So the data are never determinately implied by the deductive standard enunciated by Carnap by a theory. And so, in particular, choosing between choosing one of many hypotheses. Well, that already was inductive. But let's take a look at refuting universal hypothesis H. Well, no sample ever literally refutes a universal hypothesis because the sample is implied only with a certain probability. You can't literally verify an existential hypothesis H either because no statistical theory is literally implied by any sample, etc. Right? So all those things that used to be deductive now get classified as inductive. Okay? So at least calculation is over here. And the problem is even worse because, as a matter of fact, if you've got continuous variables, one of the points of statistics was to deal with inexact measurement or random measurement error of continuous quantities. So even our most deterministic theories, like Newtonian planetary positions, right? So Newton's gravitation theory deterministically applies to the heavens, but we have to make altitude and azimuth measurements that are not necessarily accurate, and we model that with normally distributed noise, right? So here's the normal distribution on the noise of making an observation of altitude on this quadrant. You can think of this as Tycho Brahe making measurements. So even mechanics is ultimately a stochastic theory if you take measurement error into account. Okay? So the point of that is that you just can't avoid probabilistic theories. And then the next point is that real calculations also occasion some probable error because deductive consequence is one thing. That's a formal definition of what deductively follows from what. But deductive inference is fixation of belief, right? Inference is about generating one belief from another belief, and that process is cognitive and always occasions some probable error for various reasons, failure to apply deductive rules properly, or even cosmic rays, which is interesting. I looked into it. So satellites, the integrated circuits in satellites that are, say, in the radiation belts of Jupiter, the way Voyager was, really have a significant chance of having calculation errors due to cosmic rays hitting the chips. And of course, we have that to some degree, even though it's very minimal. So there is some chance of error. And what that means is, strictly speaking, inferences based on calculation go in the right-hand side too. So now what we have is that all real inferences are inductive and none are deductive. Well, you can continue to talk with Carnap and Hume about this kind of categorization. There is a principal distinction. You could say a deductive inference is an inference that literally does accord with the rules of deduction, whether or not that ever actually occurs. But another thing to say is that a distinction that puts everything on one side is boring, right? So you can talk the other way, but maybe you'd want to refine or reform the way you talk so that you end up with a distinction that's more revealing. And that's what we're going to be doing today. Okay, so we don't want to say that all real inferences are inductive. We prefer to say something like this. So if we were going to make a first cut in philosophy, we want it to look like this. So there are ideal cases, like the ones I started with, where the distinction made some sense. That's where the data really are logically related to the theory in a nice way. But then there's a statistical case, which is the real case, where they're not. And then you'd like analogous things to be lined up in the deductive part and analogous things to be lined up in the induction part. So let's take a look. Refuting a universal hypothesis H0 in the ideal sense is very analogous, it seems intuitively, to rejecting a simple null hypothesis H0 in statistics. Right? It's like a refutation. And verifying an existential hypothesis with data is very similar to accepting a composite alternative to the null hypothesis in a statistical test. Deciding between two universal hypotheses in the ideal sense is very analogous to deciding between simple statistical hypotheses in a statistical case. Predicting E from H is like direct inference from a fully explicit statistical model in the statistical case. Inferring a universal hypothesis from data is analogous to inferring an accepted null hypothesis, which you're told not to do in the textbooks. And choosing between one of an infinite range of universal hypotheses is like model selection in statistics. Okay, so if we want the distinction between induction and deduction to be a more useful, revealing, and relevant distinction for methodology, you would want those pairwise things to end up being in the same category. Okay, so that's what we're going to try to do for you. Well, what would be a basis for this kind of sensible, methodologically sensible distinction? It would be this. So in the ideal case, a deductive method has conclusions that are stable and guaranteed to avoid error. And inductive methods produce conclusions that are unstable and not guaranteed to avoid error. I really like this picture because this is exactly the picture I have of inductive inferences. They're a house of cards. On the statistical side, all you have to say is that statistical deduction has conclusions that are stable in chance. That is to say, you have a guaranteed low chance of error in every possible world. If that's guaranteed low chance of error, and then stability is your chances of inferring that hypothesis don't go up and down radically as the sample size increases. They go up monotonically or go down monotonically. Whereas inductive statistical inferences would be unstable in chance, so your chance of producing a conclusion may go way up and then may go way down as the sample size increases. And there's no guarantee of a low chance of error. So think about accepting a null hypothesis in a statistical test. The reason you're not supposed to do it is that there's no guaranteed bound on chance of error over all possible worlds. Okay, so accepting a null hypothesis on a big sample and then inferring that hypothesis would count as induction. Okay, so that's a principled way, I think, of making the distinction. But we want to ask a deeper question than that. Otherwise, the talk would be over. What we want to ask is there a way to literally represent deductive statistical methods as deducing their conclusions from statistical information? So if you have a method, a statistical method, that's deductive in the sense we were talking about, has a guaranteed low chance of error, is there a way of talking about it as though it got some propositional information such that when the method verifies, say, the complement of a null hypothesis, you can describe it as you got some information that entails the hypothesis in the regular sense of deductive consequence, right? So can we represent statistical deduction as literal deduction from some information that we can pretend that the method got? And can we do that in a principled way? So that's what we're going to be talking about. And the answer is yes. So the first thing to talk about is on the ideal side, what is ideal information? And you might think, well, the natural place to think about information is logic. Or you might think the natural way to think about information is probability theory. I think those are the first two things that come to mind if you're trained, as I was, in philosophy of science, because that's what you're told. What I want to take a little bit of time, a little time here, to convince you of is that you'd be much better off thinking of information as topology, right? Which is something you haven't heard, but it's a very good idea. And it's gaining steam in other related areas. Okay, so how does this work? Why topology? Well, let's take a space, call the space W, and think about the points in there as not geometrical points like on this table, but think of them as possible worlds. So We're not assuming anything about the structure there. It's just a set of possible worlds, possible ways the world could be, for all you, the scientists, know. And then an information basis over the worlds. So we're going to think of this script I here as the set of possible propositional information states that the scientists could ever occupy. So there's information coming in. Each world presents some information, and so there are going to be the possible information states that you might be in as your world presents you more and more propositional information. So the question is, mathematically, what kinds of properties should the set of all possible information states have? And the first one, I think, is trivially true. Each world makes some information state true. So for every world, there's an information state in I that contains that world. So I hope it's clear we're using possible world semantics here. So truth means W is a member of the proposition it makes true, right? So P is true if and only if W is a member of it. Does that make sense? For logicians, it will. It's a fairly common way of talking. And tacitly, whenever you do Bayesian statistics, you're doing the same thing. Okay, so that's the first assumption. Why is that trivially true? It's because I'm not saying that every world presents you interesting information. If the world hasn't given you any interesting information, then you occupy the trivial information state, which is W itself. So at least W will witness this. So one, I think, is just what we mean by information. Two is a material assumption. For every pair of true information states in world W, there's an information state in world W that's at least as strong as both of them, right? That entails both of them. And how should we think of this? This is an assumption about the cumulativity of information. So it's the material assumption that by being diligent and collecting bigger samples or whatever, improving your, if you're Tycho Brahe, making your quadrants bigger, you can get more and more information about the actual world you're studying. And then if I could have gotten so-and-so, if I could have gotten information A and I could have gotten information B, then I could have gotten information that's as strong as both A and B. Okay, and so we're going to say that the local information basis at world W is just the set of all information states true in world W. So that's like all the information states I ever could have received in W is the local basis. So it's a very natural concept. In philosophy of science, we call it something like the total. If the intersection of all those would be the total information you could achieve in the limit, but you wouldn't get that by any finite stage. Okay? So here's a simple example. This is, in fact, the simplest non-trivial example that you can give. And the way it goes is we have a senior research scientist, and of course she has a lot of graduate students, so all she really cares about is whether her theory is refuted. So she has herself put to sleep with the orders that her graduate students only wake her up with a special antidote if her theory is ever refuted. So if it's never refuted, she's died happily and won't ever be bothered again. So she has a nice thought. And if it is ever refuted, she gets the relevant information because the graduate students who have been breathlessly scanning the literature all that time wake her at the relevant moment. So it's the perfect situation for a senior theorist. So what are the information states that she can occupy? Well, because of the anesthesia here, if her theory is never refuted, she's never awakened. So no information for her ever distinguishes the two states that her theory is true or her theory is false, right? Because she went to bed thinking that is true, but the information didn't guarantee that it's true. It might have been refuted at any given time, and so she only gets the information that is one or the other. If it is refuted, then she enters the information state in which the only possibility remaining is that her theory was refuted. That's what the alarm clock means. All right? And so This is sort of the most elementary possible representation of the problem of induction. Because if you were to infer that her theory is true, you'd never get information ruling out that it might be refuted later. Right? That's the asymmetry in the example. So it has a certain asymmetry. That's topological, as we'll find out. Okay, next example is more concrete. So here you're thinking about getting sequential outcomes of an experiment. So you can think of a black box as generating suggestively blue things and green things. Blue and green are the special colors for the philosophy of induction, as you all know. And so now a possible world is going to be not a point, but an infinite sequence of these outcomes. So every possible infinite sequence of these outcomes is a possible world. And an information state corresponds to what you've observed so far, right? So you can't see the infinite future, but by a given stage, you see some initial segment. So which are the possible worlds compatible with what you've seen? It's all the worlds that extend that finite segment, right? So the cone of all possible infinite extensions of what you've seen so far is exactly the information state that you're in when you've seen that many outcomes. Okay? So this corresponds to the sort of the situation of Gruen Bleen, or the sun will rise tomorrow, or bread always nourishes. Those kind of sequential examples are like this. Measurement of a real valued variable x. So here the possible world is a real number, namely the measurement that you're supposed to make if you do it correctly. But you don't get exact measurements. You can only measure accurately over an interval. So let's idealize and say that you're guaranteed to find some interval that contains the true value. Of course, in statistics, you don't have that guarantee, but we're talking about the ideal setup right now. Right? So let's idealize by saying you have confidence intervals of confidence 1 that are guaranteed to contain the true value. Then you can think of the open intervals themselves as an information basis because they satisfy the two properties that are required. Every world presents some true interval, and for any two intervals that are true of a world, you can take their intersection and you get an interval that's true of the world that entails them both. Okay? So the two axioms are satisfied there. You can do joint measurements. So here we're measuring weight as well as length. Both of those measurements are inexact. So we have a dimension here for length and a dimension for weight. And then the open interval here, cross-producted with the open interval there, gives you an open rectangle of measurements. So information states are open rectangles. Okay, so that's a joint measurement. Getting closer to interests in physics. So worlds are going to be functions. So you're looking for some function, say from reals to reals. Of course, it might be a multivariate function too, but let's just look at the unary case. Now I can make an inexact joint measurement of x and y at a given point. And since both of those are true, the function f will be incident to that open rectangle. So if I make n such observations, I'm going to have n open rectangles. And then what is my information state when I've made those three observations? It's going to be the set of all functions in the class of functions I take to be possible that are incident to each of the observations. Okay, so the information basis will be the set of all those pencils of functions. Okay, so now let's talk about deduction. It's just possible world semantics to say that H is verified by E if and only if E deductively entails H. Right? So if every world that satisfies E satisfies H, that was Carnap's definition of deductive consequence. And H is refuted by E if and only if E is a subset of the complement of H. The little C there is like set theoretic negation, right? So you're refuted if your complement is verified. And H is decided by E just in case H is either verified or refuted by E. So here's a case where the information state verifies H here's a case where the information state verifies the complement of H, which also refutes H. Okay? So it's straightforward. That's deduction. Here's a little more interesting concept. We can say that H will be verified if at a point, right? So W is a world, so here's W. We'll say that H will be verified at W just in case there's an information state that verifies H that's true in W. So if we think of W as feeding more and more information as we look harder and harder, then it's destined in W that H gets verified sooner or later, but we don't know when. Okay? And in topology, that's exactly what you mean when you say that W is an interior point of H. So interior points of H are exactly worlds in which H will be verified. Which is nice. And then in topology, there's an operation interior of H. So interior of H is just the proposition that H will be verified, because it's a set of all worlds in which H will be verified, which is the proposition that H will be verified. So you can think of interior as a modal operator that turns the proposition H into the proposition that H will be verified, which is methodologically an interesting thing to be able to do. So topology, in a sense, is the mathematics of will be verified. The exterior of H is just the dual, the proposition that H will be refuted. And the boundary of H, which is a really interesting thing, is what's left over when you take out the interior of H and the exterior of H. So that's the proposition that H will never be decided. So now we're very close to Hume's problem of induction. It turns out to be a topological feature of hypotheses. And we should all care about that as philosophers of science, so we should all care about the topology of propositions. So to expand on that theme, if you look at the part of the boundary in which H is true, so notice here, the boundary points always fall either to the complement of H or to H. They're going to be one way or the other, right? So we can now actually divide the boundary into the part that's in H or not H. So if you're in the part that's in H, those are the worlds in which H is true but will never be verified. So what is that? That's what Popper calls Hume's problem. And if you look at the rest of the boundary, that's where H is false but will never be refuted. That's what Popper calls Duhem's problem. That's the problem of a theory that you can defend forever even though it's false, and you'll never get rid of it. So it's interesting that if you go back and look at the introductory chapters of Popper's Logic of Scientific Discovery, the whole book is structured around these topological relations and dividing the boundary into those two parts. So early philosophy of science was doing topology, it just didn't know it. Okay, so now let's look at three more concepts that are a little more abstract. So think about a verifiable hypothesis as a hypothesis like an existential hypothesis that's guaranteed to be verified if it's true, right? So some raven is not black. If you think about getting an exhaustive enumeration of ravens, then if that's true, you'll eventually see a raven that's not black, and then it will be verified. So that's why the positivists said that existential hypotheses are verifiable, but universal hypotheses are only refutable. Okay? So if we understand it in that sense, which incidentally is the same exact sense that Turing uses to define semi-decidable sets, right? Recursively enumerable sets are like a proof system, so you get a one-sided yes, that's like verifiable. And co-RE sets are the ones where you get a no for sure, so those are like refutable. Right? So this is the same kind of concept that's familiar in the philosophy of mathematics as well, on the formal side. Verifiable is definable elegantly in topology as the hypothesis entails its own interior. What is the interior? It's the proposition that the hypothesis will be verified. So what do we say? A hypothesis is verifiable if it's guaranteed that if it's true, it'll be verified. But that's exactly what this condition says in topology, elegantly and without a lot of wasted words like I just did glossing it. H is refutable just in case the closure of H is a subset of H. That is to say, take the contrapositive. The contrapositive is the complement of H is a subset of the complement of the closure of H. What that says is if H is false, it will be verified, right? Because the closure of H was glossed as will never be refuted. Okay, so if H is false, then H will be refuted, is the contrapositive. That sounds like refutable. And H is decidable if it's both verifiable and refutable. So we can define these methodological concepts also in terms of topology. A verification method for H is an inference rule. So think about E as an information state, and V of E is going to be some proposition. So this is an inference rule, takes a proposition and infers some other proposition from it. So what does it take to be a verification method? In every world W, it converges to H without error if W is true, and it always concludes I don't know, which is W otherwise. Right? So if H is false, it just says I don't know. That's a one-sided test. Right? So a verifier is a one-sided test. It's like an empirical version of a Turing machine that verifies a formal predicate, which is actually where we got these ideas from. Right? We're channeling theoretical computer science here. So a verification method, just to fill that out, it may say I don't know for a while, but if H is true, then it's guaranteed to eventually start saying H. Right? And then otherwise it would never say H because it avoids error in any case. That's the sense in which it's deductive, because it's not subject to any chance of error. And then the dual is a refutation method. A refutation method for H is just a verification method for the complement of H or the negation of H. And a decision method for H converges to H or to HC without error. Okay, so it's guaranteed to come up with either answer, but never produces an error. So all of these methods are defined to be infallible in the sense that there's no chance of error. And then we'll say that H is methodologically verifiable, refutable, decidable, etc., just in case H has a method of the corresponding kind. So that's exactly parallel to computer science, right? So a set is recursively enumerable just in case there's a Turing machine that's a positive test for it. Okay, and then the relevant point here is that verification is deductive. So if V is a verifier, refuter, or decider for H, and V draws a conclusion that's non-trivial, then that conclusion is entailed by the information that it drew the conclusion on. So such methods are never ampliative, and they never fall into error. Okay, so topologically, let's relate topology to verifiability, refutability, and decidability. If we start with an information basis here, then it's a standard fact in topology that closing the basis under arbitrary disjunction or union gives you a topological space. Okay, so what we call an information basis automatically generates a topological space if you close it under arbitrary union. That sounds like a technical thing, but the proposition is not technical. It says that H is open. Well, I'm sorry. I'm not there yet. So this is just a definition. This is technical. H is open just in case H is in the closure of the possible information states, just in case H is a disjunction of possible information states, right? That's the topological definition. H is closed just in case its complement is open. And it's both closed and open, which is called clopen, if it's both closed and open, right? So clopen means both closed and open. So don't think that you can't be closed if you're open, because in general you can be both, and that's like decidability. Okay, this is what I got ahead of myself. This is what I was announcing. This is the methodological thing. So open just means verifiable, just means methodologically verifiable, right? So topologically open is just verifiability, this familiar philosophical idea. And closed is refutability, and clopen is decidability. So we've got something here that looks just like the modern theory of computability. But it's all in terms of empirical methods. And instead of computational complexity, we're talking about topological complexity. That's a very powerful idea. I didn't make it up. It's just characteristic of all work in effective descriptive set theory. So mathematicians have known about this for a long, long time, but philosophers of science haven't. Let's go back to our simplest example. So let's suppose that the hypothesis is I will never be awakened, which is equivalent to my theory is true. Right? So if the scientist went to bed happy and she's never awakened, then the verification method would just conclude the trivial thing W, because her theory has never really been verified. Right? Now, of course, she can take her own inductive risk and guess that her theory is true, but that wouldn't be verified. That would be induction. A verification method is deductive, and so it has to just sit and bide its time saying, I don't know, until such time as it becomes certain with infallibility that the theory is refuted. Okay? So that would be the verification method here. And what that says is that the upper set here, H1, is open because it's verifiable. H1 is verifiable. H0, which is the complement down here, that guy by himself, is not open because it's not verifiable. You have to do inductive inference to infer it. Neither is decidable because neither is both verifiable and refutable. Okay, so this is the reason this is the smallest non-trivial topological space. Is it's the smallest space in which you get a verifiable but not refutable proposition. If we went to a single point, then everything is decidable, obviously, because you know it already. If we go to our sequential example, H0 is, let that be the hypothesis, every outcome is green. And let H1 be the complementary hypothesis, some outcome is blue. Okay, so all outcomes are green is going to be a singleton. It's going to be exactly the infinite sequence that's always green. And then the other hypothesis will be everything else. Okay? And so let's take a look at how a method would work. Say, I don't know, I don't know, I don't know, until you see a blue outcome. And as soon as you do, say H1, which is that it's not the case that it's always green. Okay? So that verifies not always green. So not always green, which is H1 here, is verifiable. That means it's open. The complementary hypothesis, always green, it sounds like a universal hypothesis, so you'd expect it to be refutable, which is closed but not open, and that's exactly what's the case. Okay? So all of that stuff from elementary philosophy of science about verifiability and refutability is really just referring to basic topological relations in simple spaces. Okay, and so that's that was the part about ideal verifiability and ideal deduction and how it's related to topology. Now we're going to make the momentous switch to statistical verification and refutation. And so the question is, does information topology also shed light on statistically deductive methods and problems? Well, we already have a notion of deduction in statistics. It's low chance of error, right? Guaranteed low chance of error. So what we're looking for is a topology on probability measures such that open is equivalent to can verify with low chance of error. And if we had that, then we'd have a beautiful analogy to the ideal case that we could rely on intuitively to port our intuitions from basic philosophy of science over into statistics, which would be a great thing. Well, skepticism has been expressed. So in his recent book, Occam's Razors, Elliot Sober did us the compliment of saying, well, this topological stuff may be okay if the candidate theories are deductively related to the observations, but when the relationship is probabilistic, I'm skeptical. Well, I think you should be skeptical. We're skeptical, too, for all the reasons in the introduction to our talk. But if it's interesting to guess that something is impossible in print, it should be more interesting to demonstrate that it's necessary, which is what we're about to do. But since this is the hard part of the talk, I'm going to defer to my smarter colleague, and he'll take over.
Thanks, Kevin. I guess we have to go to that. So the way that we motivate, so again, what are we looking for? We're looking for topology on probability measures such that the open sets correspond to statistically verifiable things in some sense that I haven't yet spelled out. And the motivation for the topology is the same as that in the ideal situation, which is just that close by possibilities are harder to refute or rule out by statistical information. But statistical information is a kind of equivocal idea. It's unclear. We haven't told you exactly what it is. But to kind of get at it, just think of how you typically gather statistical information. You have a sample space. Every sample space in your statistics book is a metric space. Second count metric space, it doesn't really matter what that means. So what you do is you choose some event and you get a sample, and then you see whether the event occurs, right? So if you set up a statistical test, you pick an acceptance region and a rejection region, you get a sample, and then you see where the sample has landed. is with